Welcome to the Insightful Professor. In this video, we'll continue our examination of database integrity. Specifically, what we'll be doing is investigating database triggers and making a distinction between statement triggers and row triggers. We'll introduce the raise application error procedure, which is a way of signaling from within the trigger that something has gone wrong, some kind of problem has arisen. This is how we'll indicate that the statement is attempting to violate a business rule. We'll explain the firing order of triggers. We'll discuss restrictions on triggers. And in particular, we'll introduce a concept or problem referred to as a mutating table. We'll discuss compound triggers. As we talk about these topics, we'll provide examples to illustrate the concepts. As we discuss triggers, we want to be aware of some of the characteristics or properties of the triggers. First, we note that there are two types or categories of triggers. One is a statement trigger. This will fire once in response to a SQL statement, regardless of the number of rows affected by that statement. If we perform a delete operation and remove 5 rows from the table, this statement trigger will fire just one time. Another type of trigger is a row trigger. This is indicated by a special clause for each row. If we have a delete trigger which is specified as a row level trigger and we cause 5 rows to be deleted, this type of trigger will fire 5 times. It fires once for each row affected by the SQL statement. One of the benefits of the row level trigger is it gives us the ability to actually inspect the individual rows that are being affected by the operation. We can kind of look into the database and see that particular row, examine the values within the row, and then determine our course of action. So we need both kinds of triggers. And we'll talk about these with examples as we continue. But another important point is timing. When does the trigger actually execute? The DML statement will be processed, and constraints associated with the table will be enforced. When the trigger fires, we can have that occur before all of that happens. Or when the trigger fires, we could have it happen after all of those things have occurred. So the timing point becomes very critical in designing the trigger. And we'll emphasize this point with an example to show you the choice is not arbitrary. So looking at the categories and the timing points, we come up with 4 possible combinations. We can have before statement triggers, after statement triggers, before row triggers, after row triggers. Here's the syntax for a statement trigger. We say create trigger and we give it a name. The name must be unique within the schema in which the trigger is being created. We then specify the timing, either before or after. The vertical bar here gives us a choice. Do the before or do the after. The curly braces enclose our choice of options available to us. Next is the triggering event. What is the DML operation that will cause this trigger to fire? It could be delete, it could be insert, it could be update. If it's update, it also could be very specialized and address updating of a particular column rather than updating any column. Then, what is the table that the trigger is associated with? The DML event that occurs must apply to this particular table specified in the on clause. And finally, the PL SQL code that is to be performed when the trigger fires. Oracle Database allows a trigger to be written in other languages, such as Java. But our concern in this video is to illustrate the concepts of triggers and to use the language of PL/SQL. Here we provide an example of a statement trigger. First, we describe the problem. Assume we have a table called class. Each row in the class table represents one class that's scheduled for the current semester. When a class is opened and available for students to register, that is, it's not yet at capacity, there's a column in this table called closed, which will have a value of n, saying it's not closed. But when we reach capacity, we don't allow any additional students to register. So we want this column called closed to be changed to a value of y to signal that yes, it is closed, it's at capacity. So the table would look something like this. It would have a column called CNO, which would be the course number and a primary key. There would be some additional columns, and then the column to which we just referred called closed, indicating the registration capabilities for students at this point. Assume also that we have another table called seminar. In the seminar table, we record one row for each student who registers for this special course, this special seminar. The course number for the seminar is 999. The seminar must be closed when we have 75 students who register for it. That's the capacity of our seminar hall, so we cannot allow more than 75 students. What this means is once we have 75 rows in the seminar table, we want to change the value of the closed column in the class table for course number 999. We want to set this to y, indicating it's closed, and prevent further registrations. So the seminar table has information about the student who is registered for this seminar and several other columns. What we wish to do is to automate that process of changing the closed column. We're going to create a trigger which will automatically update the closed column of the class table upon reaching 75 students registered for the seminar class. Here's the code to accomplish this. We call this trigger close seminar trigger. The name is really only significant when we go to do maintenance, like disabling the trigger or altering, redefining it. We're never going to invoke this like we would regular stored procedures. Next is the timing. This will fire after an insert operation, specifically an insert on the seminar table. We have a local variable called total, which will hold the count of the number of rows in the seminar table. Within the body of this trigger, we'll execute a query to count the number of rows in the seminar table. Here's where the timing comes into play. Because this is an after trigger, the row that caused the trigger to fire, the row being inserted that caused the trigger to fire, will be reflected in this count. Had we made this a before trigger, we would only count the rows that are already in the table because the row doing the insert operation that causes the trigger to fire would not yet have been processed, therefore it will not be reflected in the count. So then we check the value in total. If it is 75, then this current insert is the 75th row. Then we perform a SQL update operation against the class table, changing the value of the closed column to y for course number 999, this seminar course. Had we defined this as a before trigger, then we would have actually had 76 students entered into the table. So the timing is important. Let's examine the timing a little more closely. When we perform a DML operation, insert, update, or delete, we could say that it occurs at a particular point in time, as shown on our timeline here. Notice that time is advancing across the screen from left to right. So prior to the DML operation, prior to the constraint enforcement, we have before. So when we create a before trigger, that's when it will fire, at the time indicated by before in our diagram. If we have an after trigger, it will execute after the DML operation has been applied and after integrity constraints have been enforced. This is really important to understand. In our previous video where we discussed constraints and introduced triggers, we created a table called employee. This table has 4 columns. I did not populate it. Let's examine the content of the table. It's currently empty. What I'm going to do is create a trigger similar to the one that I just described for the student registrations for seminar. I simply wish to stress the importance of the timing and demonstrate how that actually works. This trigger is called test count. Just a simple trigger, but it again is an after insert, and this is against the employee table. We have the same total counter variable. We're going to count the number of rows in the employee table. Remember, this code will execute after an insert operation against the employee table. And because it's after, the current row that we're inserting will be reflected in the table when we count the number of rows. So we're saying if the number is 3, display the message reached 3 rows. Otherwise, indicate it's not 3. Now let's get ready to do the inserts. I've set server output on because I'm making calls to DBMS output in the trigger. Here's an insert. Comes back not 3. Let me change this row slightly. Still not 3. And one more insert. Now it tells us that we've reached 3 rows. And there are the 3 rows. So it has counted that 3rd row that we inserted. Let's modify this by making it a before trigger. I'll undo my changes. So now the table is empty. I'll drop the trigger. And now we're back to where we started. So the change here is simply changing the timing from after to before. The rest of the code remains the same. Here's the insertion of the first row, not 3. The second row, not 3. The third row, not 3. The reason is this row is not considered part of the table at the time that the trigger executes because it executes before the DML operation is applied, as noted in our diagram. So this one, at the time we did this, would actually be only 2. If we now try to do another one, now it says reach 3 rows. But if I inspect the table, there are 4 rows. Again, this is because the trigger fired before the inserting row that caused the trigger to fire was considered to be part of the table. Next, we examine row triggers. The syntax for creating a row trigger, again, assigns a name to the trigger, specifies the timing, when it will fire, before or after the default processing, and for which event, delete, insert, or update. Update has the option of specifying specific columns. It also specifies for which table the DML operation must be applied in order for the trigger to fire. So far, it looks very similar to what we've seen with the statement level trigger. The difference comes next. We can specify that it is going to fire for each row that will be processed by the statement. This is what makes it a row-level trigger. In addition, we can specify a more precise situation, not just an insert or an update, but by specifying the when clause, we can also indicate a very specific trigger restriction, an additional condition for the trigger to fire. This condition is expressed as an SQL condition. If this condition is not met, the trigger does not fire, even though there's a DML operation being applied. Take a look at the referencing clause. The referencing clause looks a little odd. It says referencing old as, and we specify a correlation variable name. New as, and we specify another correlation variable name. The purpose for this is, in the case of an update, there is a before image. There's also an after image. We're able, with a row trigger, to look at or examine the values of the row being affected by the trigger. So we get to see what it looked like before the DML processing and what it will look like after the DML processing. The correlation variable associated with old will give us the before image, and we can use that to qualify the columns. Likewise, the correlation variable specified after new will give us the ability to qualify columns for the after effect, the after image. This particular clause is actually optional. We don't have to provide a correlation variable name for either old or new. If we choose not to include this clause, we can actually use a variable that's already defined for us called old and another variable called new. Those are the default names. And finally, we conclude the trigger declaration by providing the PL/SQL code that will execute when the trigger fires. Let's put this in context by providing a little example. Let's suppose we have two tables in an inventory management system. We have a parts table where part number, or P&O, is the primary key, and we also have some other columns that describe the parts. We have something called quantity on hand to reflect our current stock of inventory. We have minimum quantity, which is going to be effectively a trigger value to us to say, hey, we've reached the minimum, we're running out. We want to place a new order to restock our supply. And finally, when we issue the reorder request, we want to specify how many items will be included in this replacement order. Another table called pending orders. Whenever an order is placed in the system and we're waiting for that to be filled, we have the part number that is being ordered, we have the quantity that is being ordered, and we have the date that the order was placed. Our interest here is to automate the process of inserting a row into pending orders to initiate a reorder of a part for which the quantity has fallen down to our minimum quantity value. So after updating the quantity on hand column of the parts table, our goal will be to automatically have the system insert a row into pending orders, provided these two conditions are satisfied. The quantity on hand value in the parts table is such that it is now less than the minimum quantity. It's time to reorder. Additionally, there are no other rows in the pending orders table for this particular part. Assume that we didn't have this second condition. Then, once we fall below the minimum quantity threshold, we're going to place an order. Someone else comes and requests a single item for the part that we've just reordered, and again, we are below minimum quantity, we place another order. We don't want that to happen. We don't want to come in the next morning and find the parking lot filled with tractor trailers, providing us with a lifetime supply of whatever the part is. We simply want a single order that reflects that reorder quantity. So that's why we have to check this second condition. Here's how we could approach this. We say that this will fire after the update of quantity on hand on the parts table. So again, specific column being updated in the parts table, and it's an after trigger, after the update has been processed. It's a for each row trigger. It's a row level trigger. More precisely, our goal is only when the quantity on hand has fallen below the minimum quantity. And notice we use new. This is the correlation variable. New.quantity on hand. This will be the quantity on hand that is the result of the update processing. It's the after image. And once that falls below whatever the minimum quantity is, then this trigger will fire. The first thing we do is we count the number of rows in the pending orders table for part number :new.pno. :new is the default name for that table alias or correlation variable, and we use that to qualify the P&O column. Are there any rows currently in pending orders for this particular part? If there are no rows, if total is equal to 0, then we insert a new row supplying the part number, the reorder quantity, and the current date. But if total is not equal to 0, that means we already have an order in pending orders. We simply terminate the trigger. Processing is done. In this example, we've simply automated the processing, but triggers are often used to supplement integrity, to enforce business rules. So if within the processing of the trigger, we detect that the statement is violating some policy, some business rule, what should we do? How should we respond? If the trigger completes gracefully, runs to conclusion, as we did with this one, then the DML statement that caused the trigger to fire will execute successfully. And if that execution results in violating a business rule, the trigger hasn't done its job. So what the trigger needs to do is to prevent that DML processing from completing. So what we'll do is throw an exception or raise an error. That will cause the trigger to fail and also cause the triggering event, the DML operation, to fail. An error would be returned to the application that issued the DML operation. We accomplish this using a special predefined routine or procedure called raise application error. So when an exception is raised on the server, the error can be passed back to the application by invoking this procedure. So calling this procedure is similar to the idea of raising an exception with the raise statement. The current PL/SQL block, in this case the trigger body, will halt execution. Changes made by that processing will be rolled back. And this also includes aborting the DML operation that caused the trigger to fire. Now, what is different about this? It's actually rather clever how Oracle has done this. Raise application error accepts two parameters. The first one is an error number, and the second one is a text string, an error message. The error number appears to the application that receives this response as though it were an Oracle database error. the number is in the range of minus 20,000 to minus 20,999. If you look in the Oracle documentation, ORA error messages within this range have been reserved for an installation. They're user-defined error numbers. The error message will be a string of characters, up to 2,000 characters, that will be returned to the application, appended to that error message. But the interesting thing about this is this works within the same framework as a regular system-detected error message that you would find in the database messages documentation. So within the application that performs the DML operation that subsequently causes the trigger to fire and signal an exception, the error number can be accessed by using the SQL code, the SQL code function that Oracle has provided, and the error message can be accessed by using the SQL error message function, SQL ERRM. Because this is, for all practical purposes, a message that is generated through the error processing mechanism within the database management system. Here's an example to illustrate this. It's not a great way to use a trigger because we could accomplish the same thing that this trigger is doing with a simple declarative check constraint. But we want to provide a simple example to illustrate the idea of raise application error and how it causes the trigger to fail and also the DML operation to fail. So here we create a trigger called check fee, which will fire before the insert processing on the course table. It is a row-level trigger which allows us to gain access to the actual values contained within the record. Now, the user is attempting to insert a record into the course table. What we're going to do is to check the value that they've provided for the lab fee. And if the lab fee exceeds an established maximum of 500 or falls below a minimum of 0, then this is not an acceptable lab fee. It's either way too much or it's negative, which means we're paying a student to take the course. The administration frowns upon that. So therefore, if we detect this problem, what will happen is we'll throw the exception or raise an error. And we've chosen a number minus 20,100, one of the values allowed within that range, and we put out a message lab fee out of range. Notice that we're using the correlation variable of new because we're inserting a new record. That's what insert does. And we're looking at the lab fee within this record and interrogating it. If from SQL Plus or SQL Developer, an interactive tool for submitting SQL, we attempt to execute an insert where we're inserting a value of minus 100 for the lab fee, the trigger will receive this, it will interrogate it, and we saw that the conditional statement, the if statement, says, oh, this is not allowed, and it throws the exception or raises the application error, and here's the error message. ORA minus 20,100, lab fee out of range. And if you look in the Oracle messages documentation, this message is not there. This was developed by our application. So if we're using this in applications that we develop in-house systems, then what we want to do is we want to document each of these messages because they will not be documented within Oracle documentation because we made these up. Although it's possible to have more than one trigger associated with a table, it is also sometimes more practical to create a single program unit, one trigger, that could fire in response to different events. Here's an example where we say we're creating a trigger check fee, which will fire before an insert or an update on the course table. Either one of these two events will cause this trigger to fire. Within the trigger, how do we know whether it was an insert or an update operation? Oracle conveniently provides conditional predicates that can be used to determine which event actually caused the trigger to fire. Inserting, if an insert statement was the cause of the trigger firing. Updating. Deleting. A conditional predicate, such as inserting, updating, can appear wherever a Boolean expression can appear. So these predicates can be tested with an if statement to determine the logic path to follow within the code of the trigger body. Here's the example in a little bit more detail of that trigger called check fee. This will fire in response to an insert or an update of the lab fee column. We check to see if inserting was the cause. Was it an insert statement? If so, we take appropriate action. If it was not inserting, we check to see if it was updating. If it was updating, we take this course of action. Another useful application of a trigger is to derive a value based on whatever information might be available. If we were inserting a row into the table, perhaps the user cannot supply the C department column. They can supply values for all of the other columns, but not C department. What we'd like to do is automatically generate the appropriate value for this column based upon other information that was provided by the user. In this trigger, we examine the C department column of the new record being constructed. This is an insert operation. If it's null, which means that the user did not provide the value, then what we do is we use the course number to determine the department. All computer science courses begin with the letter C. All theology courses begin with the letter T. All philosophy courses begin with the letter P. Perhaps it's a silly example, but it illustrates the idea of how we can automatically supply a value for a column that the user did not supply a value for, perhaps because they were unable to. We've indicated that you could have more than one trigger associated with a table. You could have a different trigger for each DML statement. There could be an insert trigger, an update trigger, a delete trigger. But it's also possible to have more than one trigger associated with a DML operation. We could have more than one insert trigger, more than one update trigger, more than one delete trigger. What I'm getting at here is there's something called the timing point. When does the trigger actually fire or execute? Remember that we have two broad categories of triggers, statement triggers and row triggers. Let's take a closer look at the firing order or timing point. We could have a before statement trigger. If we do an insert, update, delete, and we have a before statement trigger, this will be the first trigger to fire. Then, for each row affected by the DML operation, we'll have the row triggers fire. We'll have the before row trigger fire. Then, the statement will be executed, and then the after row trigger fires. This will be repeated for each row affected by the DML statement. Finally, after all of the row triggers have been executed, we'll have the after statement trigger fire. Taking this all together, we say a single table could have more than one trigger of each type, allowing for more than 12 triggers for a table. Note that if a table has more than one trigger of the same type, the firing order of these triggers cannot be determined before execution. Rather than have separate triggers for each timing point, it's possible to consolidate some of these triggers. We have a special type of trigger available called a compound trigger. The triggers we've been referring to thus far could be called simple triggers. They fire at exactly one of the timing points we've described. before the triggering event executes, after the triggering event executes, before each row affected by the event, or after each row affected by the event. With a compound trigger, it's a bit different. A compound trigger has potentially 4 distinct sections associated with the 4 timing points. In addition, a compound trigger has a declaration section where variables or work areas can be declared, and they would then be shared by the different timing point sections. So we would have something called before statement as a section, before each row as a section, and likewise for after each row and after statement. Now it's possible that we have all 4 of these sections or only one of the sections. All sections have the ability to access this common declaration section. So when the triggering statement starts, these work areas or variables in the declaration section, they come into existence, they could be populated, and we can refer to them in the code for each of the timing points. If we had 4 distinct simple triggers, they wouldn't share the same storage area. Any variables declared in the before statement trigger would not be available to the after statement trigger or the before row or the after row trigger. So this is an interesting way to think about structuring the code. Here's the basic syntax. We would say create trigger, give a name to it, and we would then say for DML event. We've seen the DML event clause in our examination of both statement and row DML triggers in the simple triggers. It identifies the triggering DML operation and the table against which this operation must be performed to cause the trigger to fire. In this context, for the compound trigger, we introduce the DML event with the word for rather than with a timing before or after. The reason we don't need the before or after is these points will be declared elsewhere within the timing point section. Note the keywords compound trigger. This is what clearly informs the system that this is a compound trigger rather than a simple trigger. These keywords precede our declaration section and also the introduction of the timing points of the trigger. Note that if a trigger has multiple timing point sections, they can be coded in any order. We don't have to list them such that we say before statement, before row, after statement. They can be coded in any order. To introduce these sections, we would follow this convention. We would use the timing point name, before statement, follow that by the word is, and then we would have a begin-end block which contains the executable code for that section, for that timing point. We also wrap this up with the label before statement appended to the end. Similarly, if we had before each row, we would again say before each row is, the begin, end, and the end would include the timing point before each row. And the same would be true for the other 2 timing points. So why would we have a compound trigger? Well, for one thing, we could consolidate code. We also indicated that we could share the declarations between the different timing point sections. A compound trigger is useful to avoid a special situation that can arise called a mutating table. A mutating table is a table that is being modified by a DML statement. A problem arises when a row trigger associated with a table tries to access that table through a query or tries to modify the content of the same table within the trigger. Because the table is said to be in a state of change, it's said to be mutating, the system responds with an error message. A compound trigger can provide a solution to this problem. In an earlier demonstration, we had looked at the difference in behavior between a before trigger and an after trigger. We're going to use that same idea to examine some of the characteristics of a compound trigger. We have two tables that we've been using, employee and department. The employee table is currently empty. I'm going to populate it, but prior to doing that, I'm going to create a compound trigger that will demonstrate the timing points, and it will also demonstrate the use of a shared declaration area. Here's the trigger called test count, which will fire based on an insert operation for employee. Because it's a compound trigger, line 2 simply says it's associated with an insert, and there's no timing factor here. Line 3 confirms it's a compound trigger. Line 7 introduces the before statement timing point, and line 15 introduces the after statement timing point. Effectively, we've combined two separate triggers into one by using this compound trigger mechanism. On line 5, we have a variable that could be considered a global variable. It's accessible to the code within the before statement timing point and also to the code within the after statement timing point. Even though these sections of code will execute at different times, it's as though test count is fired up to perform the before statement processing, and then it ends. It's fired up again when the after statement point in time arises, and it starts processing that code. But it doesn't really end. We could almost think of it as being suspended, because what's happening is the state of the variables, this variable called total on line 5, is brought into existence when the triggering event occurs. It's accessible within the before statement timing block, and it's also accessible with the same state being preserved when we get to the after statement timing block. Prior to populating, let's look at what's going to happen. When the before statement timing point arrives, we make a call to DBMS output and display the value of this variable total. Now, the variable was intentionally not initialized on line 5. Therefore, it has a value of null at this point. Then we count the number of rows currently in employee, which we know to be 0. We examined the table already, and place that value in this variable. And then on line 13, we display the value of the variable, which will be 0 because there are no rows in the table. Then the statement is processed. And then the after statement timing point arrives, and we execute the code starting on line 16. Here, we display the value of total, which will have the same value that it had when the before statement timing point block completed. It will not be null, but it will be 0. Then we count the number of rows. Now the row that caused the triggering event to occur will be reflected in the count, and what we'll see is on line 21, we'll display the value of 1. Let's set server output on, because we're using DBMS output, perform an insert, and we have the value of the variable, and it shows nothing. The value is null because we did not initialize it. Then comes the number of rows, being 0. These two lines were executed in the before statement timing point block. Then the insert statement actually executed and the row was inserted into the table. These last two lines of output reflect the processing of the after statement. Let's try this again. And notice the trigger fires again, but this time in the before statement block, the number of rows already in the table is 1. That's our first row that we inserted at the top of my display here. And then the effect of inserting this row with the second insert brings the number up to 2. Hopefully you get the idea of consolidating the multiple processes, the different timing points, into a single program unit, but also the ability to share code and kind of pass data from one timing point block to another timing point block. This is really quite powerful. We've mentioned the problem of a mutating table and indicated that a compound trigger could easily resolve this issue, but we haven't really demonstrated what this problem is. We're going to do that now. Remember that we have these two tables, employee and department. Let's review their structure and the content. I'm starting with a blank slate once again. So the department table has 4 columns. Primary key is DEPT. We insert a row in there for the philosophy department. We have the second table, employee, which has a primary key of employee number, and DEPT ID is the foreign key, giving us referential integrity. We insert a row in there, employee number 123, assigned to the philosophy department, complying with referential integrity. We apply the changes with commit. So let's examine these two tables to confirm the content. Department does indeed have the philosophy row we inserted. An employee has the row for Mo, employee number 123, assigned to the philosophy department. Now we're ready to demonstrate the idea of a mutating table, a problem that arises within a row-level trigger. Our intention here is to delete an employee and have a trigger kind of acknowledge that deletion by simply displaying on the screen the employee number and the employee name of the employee who was deleted, and also to then take an assessment as to how many employees remain in the table. We do this as an after delete because we want to see the effect of this deletion. So the problem arises when we attempt to do the select on line 10. We're counting the number of rows from the employee table. The employee table is the table against which the DML operation is being applied. This is where the problem arises. The trigger is created, the code compiles successfully, but what happens when we attempt to perform this delete? Here's the triggering statement. Delete from employee, specifically employee number 123. This fails, but notice the message. It says that the table employee is mutating. It further states that this trigger or this function might not see the exact content of the table because it's in a state of change or flux. It's mutating. It further tells us that the actual error occurs in a specific line within the trigger. So it tells us the trigger that caused the problem. Let's take a look at a solution using a compound trigger. We'll start with a blank slate. We remove the existing trigger, empty out the employee table, empty the department table, apply these changes, and now we're ready to create our compound trigger. Remember the syntax. We're saying this is for the delete operation on the employee table. Line 3 tells us it's a compound trigger. In our declaration section, we declare a variable that will be used to hold the count, and then we have our first timing point before each row. All we can do within this is examine the content of the row being deleted. So we simply display with calls to DBMS output the employee number and employee name of the row being deleted. We're done. Remember, we cannot look at the table. The after statement is the second timing point, and here we count the number of rows in the table. We have access to the table. We can run queries against the table with a statement level trigger. We obtain that number, put it into our variable, and then we make the call to dbms output to display the value that we found. Trigger gets created. Let's go ahead and try this. We put our 2 rows that we worked with previously into the table. We confirm that those rows have been inserted. We'll attempt to delete row 1, 2, 3, just as we did before. This time, it's successful. We get the report that 1, 2, 3 is the employee number, Mo is the employee, and currently there are 0 employees in the table. And now we'll do a little housekeeping just to clean things up. But that shows us how the compound trigger can address the problem of avoiding the mutating table. Without the compound trigger, we would need to create 2 distinct triggers. We would have to have a before row level trigger to obtain the information that we found about the employee being deleted. We would also have to have an after statement level trigger to be able to do the count, including the effect of the row that caused the triggers to fire. If it was necessary to pass information between the 2 triggers, we would need another mechanism, something called a package. We would actually need 3 program objects in order to implement what we were able to do here with a single program object, the compound trigger. Because a trigger implements procedural integrity, there is some process or program that executes to implement our business rule or enforce our business rule. It's possible to suspend the execution of this program. What we could do is disable the trigger's execution. This is accomplished with an alter statement. By default, when a trigger is created using the create trigger statement, the trigger is placed in an enabled state. Once the trigger has been created, it will automatically enforce the business rule it was designed to enforce. But there are reasons which we might consider for temporarily suspending the execution of the trigger, disabling it. The trigger could refer to an unavailable object. You might have to do a large load of data with a load utility, and you don't want the trigger to fire for each one of the rows being processed. Therefore, you can speed up the load process by disabling the trigger. One thing to keep in mind is that if the trigger is disabled, then the business rule that it was designed to enforce is not being enforced. So if you're loading data into a table and the trigger has been disabled, you could actually get data that violates the business rule into a table. So keep in mind that the data must be validated in some way, because once the trigger is turned on later after the fact, it doesn't go back and look at what's already in the table. We'll give a little demonstration of this in a moment. So we can alter a trigger with the alter trigger statement to enable or disable a single trigger. If a table has multiple triggers associated with it, we can do this all at once with an alter table statement. We can alter table, enable, or disable all of the triggers associated with that table. I've connected to the database as a different user, a user that owns the course table. We've discussed the course table in previous videos. We took a look at the concept of this trigger called check fee, which would be a way of controlling the range of values allowed in the lab fee column of the course table. We'll now use that trigger to demonstrate the enable and disable capabilities. The content of the course table includes these 14 rows, but what I want to draw your attention to is the C lab fee column. The values in this column all conform to the rule that we described. Values are permitted between 0 and 500. Currently, we don't have the trigger. We were just trusting our users, or perhaps doing data validation within an application. to ensure that values would be between 0 and 500. Let me attempt to insert a row into the table where I put values of, and we'll just pick something like C77, call it new, the description is new, credit is 3, the lab fee is $999. It's accepted. That's because there's currently no integrity. There's no declarative integrity, no check constraint, nor is there a trigger. So we can put any value we want in there. Let's remove that row. Let's now consider the trigger. We've created the trigger, as we've described earlier, which imposes the constraint that the lab fee must be between 0 and 500. Now, the value of 999 is rejected by the trigger. So we've implemented our integrity. Let's disable this trigger. We'll alter trigger check fee disable. Now let's attempt to do this insert. The insert is allowed. Now we'll turn the trigger back on. The trigger is altered, and what do we have in the table? We have that row with an invalid lab fee. We could think of the trigger as kind of being a guard standing at a gate. The guard leaves his position, someone can just walk through the gate. And that's what happened. This row got in. So the trigger, once it's enabled, or once it's created, does not look back to see what's already in the table. It's an important point about how procedural integrity works. There are some additional restrictions associated with triggers. We perhaps touched upon a little bit of this already, but let's expand on it. There's a size restriction. A trigger cannot exceed 32K. That's a pretty sizable chunk of code. But if the logic of a trigger requires many statements, it's possible to extract some of those statements and place them in a stored procedure, and then from within the trigger, invoke that stored procedure. That way we could stay within the 32K limit if the business logic was that complex. Also, the long and long raw data types, these are being phased out by Oracle. They're supported for backward compatibility, but Oracle wants you to use large objects instead. What we have, and we've had this for quite some time, even before large objects were coming in and long was being phased out, we have some restrictions that say a trigger cannot declare a variable of the long or long raw data type, and there are some other restrictions. So you probably just want to stay clear of this data type or these data types anyway. The mutating table restriction, we've talked briefly about that and demonstrated its behavior. There are also limitations on the use of transaction control, commit, rollback, save point, and data definition statements within a trigger. In order to execute these within a trigger, we would have to have what is called an autonomous transaction. And that's something we've not discussed in this video. If you're curious about that, add a comment to this video and we can investigate that as a separate video. Kind of an interesting concept. To summarize the create trigger statement, what this does is it creates or replaces a database trigger. If we simply say create trigger, the trigger must not already be defined, it gets created. But if we say create or replace trigger, if the trigger already exists, we're replacing its definition. A trigger has the following basic components that we've described: a trigger name, a trigger event, a trigger restriction, and finally the trigger action. The way Oracle deals with PL/SQL triggers is they'll be compiled and stored within the database, just like PL/SQL stored procedures. So what have we discussed in this video? We've distinguished statement triggers from row triggers. We have identified a variety of applications of triggers and provided some examples. we've introduced the raise application error procedure for signaling a problem from within a trigger. We explained the firing order of triggers. We explained some problems, including the mutating table, and demonstrated how that problem occurs and how it can be addressed. Specifically, we discussed compound triggers and provided a solution to the mutating table problem using compound triggers. I hope you found the video to be helpful and informative, and if you did, consider giving us a thumbs up. Furthermore, consider subscribing to the channel to be notified when we add additional videos. And once again, thanks for watching.